Today is still section 11.3, but we're going to do day 3. We're actually going to do some calculus on these polar functions. Okay, so what is the slope of a polar curve? All right, so we know the slope of a function in terms of y and x is dy dx, but now your polar curve is going to be some function defined in terms of theta. So it'll be dy d theta divided by dx d theta. So keep in mind they're going to give you some polar curve. You're going to change it to parametric form, which is what we gave you right at the end of day 2's lesson, and then you'll take the derivative. So make sure you transform it into parametric mode first. Remember, derivative is what's going to give you the slope. So the first example says, let's find the slope of the rose curve. That's like those petal graphs. R equals 2 sine of 3 theta. 3 is what's telling you there's going to be 3 petals there, at the point where theta equals pi over 6, and use it to find the equation of the tangent line. So the first thing we're going to do is change this to parametric, right? Because r is in terms of theta. R is in terms of theta, right? But we want dy dx, right? So we want dy d theta and dx d theta. So first of all, we know x is equal to r times cosine of theta. But then remember at the end of yesterday's lesson, I said, hey, r is going to be given to you as some function of theta. This is f of theta. So we replace r with f of theta, and it's this guy, right? R is f of theta, and it's 2 sine of 3 theta. So I'm going to replace this f of theta with 2 sine of 3 theta, and then I still have the times cosine of theta from this guy here. So x is going to be 2 sine of 3 theta times cosine of theta. Y, if you remember, is r times sine of theta. And again, r is some function of theta, and in this case, it's 2 sine of 3 theta. So we've got that y will be 2 times sine of 3 theta, and then times sine of theta. Okay, now we're ready to take the derivative. Now we can take dy in terms of theta, dy d theta, and then also dx in terms of theta. So I'm going to go to a new slide, and this new slide has the x equals this and the y equals that already on there. All right, so x is equal to 2 sine of 3 theta times cosine of theta. Y equals 2 sine of 3 theta times sine of theta. And now when we find dy dx, we'll do dy d theta over dx d theta and dy d theta. All right, we're going to take the derivative of this guy, and that's product. That you got to do product rule because you've got a function times another function, right? So we're taking the derivative of, well, I'm taking the function, the first guy, 2 sine of 3 theta, and then times the derivative of sine, which gives you cosine. And then remember, plus, and then we'll take the derivative of the first and then just times the second guy. The derivative of the first guy, this is just a constant. Derivative of sine of 3 theta would be cosine of 3 theta. But then chain rule would say, you got a 3 theta there, so multiply it times 3. So that ends up becoming a plus 6 times cosine of 3 theta and then times sine of theta. You need to do the same thing with x, taking the derivative of x, but with respect to theta. And again, you've got product rule happening. So I'm going to take the first guy, just leave it alone, 2 sine of 3 theta, and then times the derivative of cosine. Derivative of cosine is negative sine. So I threw that negative in front here. That's how I get the negative there, because it was truly a positive 2 sine of 3 theta times negative sine, and I just pulled that negative out front. And then it's plus cosine times the derivative of this guy. So derivative of that guy, the 2 is just a constant, so it would stay there. Derivative of sine is cosine of 3 theta. The chain rule would say times this 3, and 3 times 2 will give you 6. So it's a plus 6 times cosine of 3 theta, and then times cosine of theta. All right, now we want to know what is the slope of this curve at the point when theta is pi over 6. So evaluate this at pi over 6. So in all of these thetas, I'm going to plug in a pi over 6 and evaluate it. So I would have a 2. I would have sine of 3 times pi over 6, which when you simplified it, it's pi over 2. So you'll have a sine of pi over 2, and then a cosine of pi over 6. So you have 2, sine of pi over 2 would be 1, and cosine of pi over 6 would be read 3 over 2. Then you'll have a plus sign and a 6, and then plugging pi over 6 in here, you're looking at cosine of pi over 2. Well, that'll be 0. And then sine of pi over 6, if you remember, is 1/2. So that's where I'm getting the 6 times 0 and then times 1/2. On the bottom, you'll have a negative 2, sine of pi over 2, so that'll be a 1, and then sine of pi over 6, which is a 1/2. So you'll have negative 2 times 1 times 1/2, and then a plus 6 times cosine of pi over 2, that'll be 0. Cosine of pi over 6 is read 3 over 2. So obviously when you multiply 0 times the 6 and times this 1/2, that's going to 0 out and cancel, and 6 times 0 times read 3 over 2, that'll cancel. So you're left with 2 times 1 times read 3 over 2, and negative 2 times 1 times 1/2. These 2's cancel, those 2's cancel. I think I cancel them in a different order, but those guys cancel, so do those guys. You're left with a negative read 3. That is the slope of this petal curve or rose curve right at the point when theta is equal to pi over 6. All right, then it says now use this slope to find the equation of the tangent line. So to find an equation of a line, you need a slope. We got it. Whoop, whoop. You also need a point. Yeah, and we're going to get the point in x and y. Keep in mind, x is equal to 2 sine of 3 theta cosine of theta. And we're wanting to know at theta equals pi over 6. So we're going to plug this pi over 6 into each of those and figure out what the x value is. Y is equal to 2 sine of 3 theta times sine of theta, plugging theta equals pi over 6 into both of these guys, and then we'll figure out what y is. So next slide, we have the same guys there. We're going to actually figure out what are the x and y values when theta is pi over 6. We're going to get them in rectangular coordinates. All right, so your x is 2 times sine of 3 pi over 6, which is pi over 2, times cosine of pi over 6. And that'll give you a 2 times 1 times read 3 over 2, which will give you a read 3. And then your y, you do the same thing, plugging in pi over 6 and plugging in pi over 6. So 3 pi over 6 leaves you with the pi over 2 here. And so that leaves you with a 2 times 1 times 1/2, which leaves you with a 1. So your rectangular coordinate at when theta is pi over 6 is going to be rad 3 and a 1. And so the point is rad 3 comma 1. And then you put it in point slope form. Y minus y1, that's the 1 coming right here, equals the slope, negative 3, times the quantity x minus this x1. And there is the equation of the tangent line at that point when theta is pi over 6. All right, there's that. And then we go and find area enclosed by polar curves. All right, so we want a formula that allows for small sectors of areas instead of small rectangles of areas. You know, when we were in rectangular, and we had this curve, we used rectangulars, but we were in rectangular form, right? We were in the Cartesian plane where rectangles made sense. Now we're in polar curves where we're talking about r's and thetas, right? We're talking about circles. And so instead, you'll have some polar curve, and we're talking about the area of a sector instead. remember the area of a sector. So here, if the whole circle's going around, we can take just this slice of the pie, and that's the area of a sector, or a wedge sometimes they're called. And if you remember the area, if you don't, it's an easy derivation from just taking a proportion of the whole circle and then times the area of the circle. And so you end up with 1/2 r squared theta. And the derivative, dA, is going to be with respect to theta. And so and then your r will end up being defined in terms of theta, right? So just so you know, that's the reason why we've got 1/2 r squared theta. And when you take the derivative of this guy with respect to theta, it'll be just 1/2 r squared d theta. But then r is going to be some function of theta. All right, so let's give you the formula now to find the area, right, of the area. If we know this guy, we're going to integrate it. So the area of the region between the origin, so the area of the region between the origin and the polar curve. The polar curve will be given as r equals some function of theta, where theta is between alpha and beta. The area will be the integral from alpha to beta of 1/2 r squared d theta. Now keep in mind your r is going to be defined in terms of some function of theta. So I'm going to replace that r with the f of theta. So whatever rule they give me for r, whatever that equation is, that's what you're going to plug in here and you're going to square it. I pulled the 1/2 out front, and then we're going to integrate it with respect to theta. Let's do an example where we want to find the area of the region enclosed by the cardioid, r equals 2 times the quantity 1 plus cosine of theta. So that's not written how you're used to seeing it. You're used to seeing it with the 2 distributed. So your book gives it like this. You're going to distribute that 2 in there. Here's what you're used to seeing, right? I've got a 2 and a 2, same number, nice steady heartbeat. Tells you that this is a cardioid. The directions also told you it's a cardioid. Whatever. We know it's oriented on the x-axis, or it's technically called the positive polar axis. We know it's oriented to the right, and we know that large diameter would be 2 plus 2 is 4, and then the bumps, what you mark on the other axis, on the y-axis, will be 2 and 2. So here's a picture. Right, you got a point at the origin, 4 units to the right, put a dot, 2 units up, put a dot, put down 2, put a dot, and then you create this nice curvy cardioid. And we want the area of the region enclosed by this. So we want the area of the entire inside of this cardioid. And so we're using this formula here. We got the area is equal to 1/2. This cardioid is generated from all the way from 0 to 2 pi. If you plug in a 0 into theta, you would get cosine of 0 is 1, 2 plus 2 is 4. So when theta is 0, you're starting here. And if you were to plug in values, just real friendly ones, easy ones, you'll see that this cardioid is generated by, as you go around from 0 to 2 pi, it starts here and it'll go around this way. If you plug it into your graphing calculator, and you watch how it's traced out, you'll see that it starts here and then it goes around and curves and all the way. So a cardioid, you'll go from 0 to 2 pi. And then you're plugging that in. Don't forget to square it. I'm going to show you how to do this by hand on this example. Other ones will just do a quick FN int, but you can evaluate this by hand. You first need to expand that. So when you square it, you'll have 2 squared plus 2 times 2 times 2 cosine theta, which is where we get the plus 8 cosine theta, and then plus the quantity 2 cosine theta, quantity squared, so that's where we get the 4 cosine squared theta. And we want to find the antiderivative of this. This guy's easy to find. This guy's easy to find. This guy, not so much. Not with that cosine squared. You have a function inside of another function. But, okay. Hopefully you're good. I've got this line on the next slide, so I'm going to the next slide. All right, but here's what we can use. We can use the Pythagorean identities from trig that said cosine of 2 theta was equal to 2 cosine squared minus 1. I just rewrote it and solved for cosine squared. This is not the first time you're seeing this in this class. I've talked about this before, that anytime you had a cosine squared or a sine squared, you would use the Pythagorean, the double angle. I said Pythagorean. It's the double angle identity, cosine of 2 theta. You would use this double angle identity to rewrite this squared so that it's no longer a function inside of another function. Right, so that's what we're going to do here. I'm going to replace this cosine squared with this identity. It's the double angle identity. Notice, oh, here's what else I did. I saw the 1/2 and I saw 4, 8, and 4 were all multiples of 2. So I went ahead and distributed that 1/2 so I didn't have to keep that 1/2 out front, and I divided 4 by 2 and 8 by 2 and also 4 by 2. That's where I'm getting the 2 and the 4 and the 2 now. And then instead of cosine squared here, I replaced it with 1 plus cosine of 2 theta divided by 2. So now these 2's will cancel. And, all right, so the 2's cancel, and I'd be left with just the 1 plus cosine of 2 theta. And I went ahead and took this 1 and I added it to the constant 2. So that's where I'm getting the 3. These 2's canceled, and then this 1 got added to the 2 to become a 3. So now I'm finding the antiderivative of this, and that is a totally doable problem for you. Antiderivative of 3 is 3 theta. Antiderivative of 4 cosine theta would be 4 sine of theta. Antiderivative of cosine of 2 theta would be, antiderivative of cosine is sine of 2 theta, but chain rule would have said we would have had to multiply by a 2 when we're taking the derivative. So we need to undo that by multiplying by 1/2. And sure enough, if you go and you take the derivative of this guy, you'd have derivative of sine is cosine, but then times 2 times 1/2 would undo that, and it would just be a 1. All right, so there we go. There's the antiderivative of that. We're evaluating it from 0 to 2 pi. Remember, you plug in the upper limit first, so plugging in 2 pi first, you'll have a 3 times 2 pi, which is 6 pi. Sine of 2 pi is 0. Sine of 4 pi, also 0. So this part right here was the plugging in the 2 pi. When you plug in a 0, 0, sine of 0 is 0. Sine of 2 times 0, still 0. So all of those guys ended up being 0, and you end up with the area inside that cardioid is 6 pi. Okay, so that is how you handle when there is a squared. Same thing with sine squared. Use that double angle identity, but for sine. For sine squared. Okay, let's do another one. More complicated one. We're going to find the area inside the smaller loop of the limison, r equals 1 plus 2 cosine theta. So they give us the hint that it's a limison, but we would have known that because 1 is smaller than 2. And when the number in front here is smaller than this guy, then it's a loop-de-loop limison. Cosine, it's oriented on the x-axis or the polar axis, oriented to the right. And your larger diameter would be 1 plus 2, which is 3. You'd go out 3 units, put a dot on the positive x-axis, 3 circles out, 3 r's out, right? The inner loop would be 2 minus 1. So 1 unit out, you'll put the dot for the inner loop. You'll have a dot at the origin or the pole. And then the 1 are what we call the bumps, and that's what you're going to put on the y-axis. So there you go. 3 units out, going at the pole or the origin, 1 unit out for the inner loop, bumps are at 1 and negative 1, and do. All right, so we want the area of just inside this inner loop. Now, it's important to point out that polar graphing is different from rectangular graphing, right? You're plugging in angles. So if we start with when theta is 0, cosine of 0 would be 1. So that's 2 plus 1 gives you 3. This graph, when theta is 0, starts right here. And then you can plug in more. Like if you plugged in pi over 6, that would be rod 3 over 2. How about pi over 3 would give you a 1/2. And so that would be a 1 plus 1. So right here, it corresponds to pi over 3. Keep in mind my window is kind of stretched horizontally right there to make it look not deformed, right? Okay, so so basically my point is this. The way that a looped limison is generated is it starts here, and then it goes around, and it loop-de-loops, and it loop-de-loops, and it comes around like that. And if you watch a graphing calculator, it actually, like the first time you hit graph, and it traces it out, you'll see it does it in that order. This is from 0 to 2 pi, all the way, if we wanted the whole area, right? But we only want this guy. So what do I care about? I care about right here and right, like, I want to know, like, when is this guy being 0, right? When is my radius? When is my R value 0? Because this guy is going to come around, hit the 0 here, so whatever angle that is, and then it's going to keep on going and then hit 0 again, right? All right, so we want to find the values when R is 0, because that's going to give you whoopie doopie doo. Crazy buttons. Sorry about that. That's what's going to give you the angles for your limits of integration, right? Because we only want, this guy traces along. Don't care about all that area. I care about the area that starts right here and is generated by going around to just there. We set this guy equal to 0 and subtract 1, divide by 2. Cosine is negative 1/2 when theta is 2 pi over 3. And also when theta is 4 pi over 3. And sure enough, if you plugged those values in, 2 pi over 3 would give you a negative 1/2. So 1 plus negative 1/2 gives you the 0. So totally makes sense that 2 pi over 3, same thing, 4 pi over, cosine of 4 pi over 3 is also negative 1/2. So those are the values that are going to generate this little loop-de-loop. Well, the starting and ending point of it. That makes sense. All right, so and in the area, we've got 1/2. The 2 pi over 3 and the 4 pi over 3 are what are giving me my limits of integration. That's the starting point of that loop and the ending point of that loop. And then plugging in here is your R, replacing it with 1 plus 2 cosine of theta, and then quantity squared, and then d theta. This time I'm going to cheat, and we're just going to put it in our calculator. You could do this by hand, just like we did the last one, and it's fine. But for time, let's just do fn int. And when you put that in your calculator, you will get 0.544. All right. Hopefully that makes sense. All right. And let's go and take it another step further. We're going to find the area between two polar curves. All right, so the area between two polar curves. So here's one function, R1, and another function, R2, both of them in terms of theta. Theta is between alpha and beta. Then the area between these two curves is going to be, it's the same guy, right? If you cover up this part, it's from alpha to beta, 1/2 r squared d theta. But you're going to take r2 squared and then subtract from it the integral of 1/2 r1 squared. And what are R2 and R1? Well, okay, well, before I get to that, you can simplify this, right? It's the subtraction of, you've got the same limits, you're subtracting them. Properties of limit says, hey, I can pull that 1/2 out front, take the integral from just alpha to beta of the R2 squared minus R1 squared, d theta. So that's what we're going to end up using. It's just a fast route. You could do it separately, but you can combine them into the same integral, which which is what we'll do. Keep in mind, when I say R2 and I say R1, you need to figure out which one is the outside curve and which one is the inside curve of whatever this is shaded. You're going to look at that. You're going to graph the two curves. You're going to shade the part they want. And then of the shading of the area they want you to find, what's the outside curve and what's the inside curve. Like as you draw, like sectors coming out from the origin is how you should think about it, right? You're drawing sectors coming out. All right. So let's do an example. We're going to find the area of the region that lies between the circle r equals 1. R equals 1 is a circle that's centered at the origin with a radius of 1. And so that lies inside the circle, but outside the cardioid, 1 minus cosine theta. So you know what that looks like? This is the cardioid cosine, so it's oriented on the x-axis. Negative means its biggest diameter is over on the left side of the origin. And you'll go, there's an invisible little 1 right there. So your large diameter will be 1 plus 1, so 2 units to the left. And then your bumps will be at 1 and negative 1. So here are the two graphs. The red one is the circle of r equals 1. The blue guy is I went out 2 units to the left, 1 unit up, 1 unit down. And we want the area of the region that lies in the circle inside this circle, but outside the cardioid, which leaves me with this little yellow shaded piece right there. That's the area we want to find. All right. Symmetry is going to allow me to simplify this some. I don't need to do this whole area. What I'm going to do instead is find just half of it. Oh, I guess before I say that, okay, when you're looking at this shaded area, change to a pen. When you're looking at the shaded area, let's go with blue. Okay. Oh, blue is already there. How about, all right, I'm sticking with blue. When you're talking about which one is outside and which one is inside, I hope you can see from this which one's outside and which one's inside, but it's as you draw sectors or lines radiating out from the origin to each of these guys. Yeah, you're hitting the outside and you're hitting an inside point, right? So each of these lines, as you're drawing these little, remember, we're not making rectangles now, we're making sectors of circles. So as you draw these make little sectors and divide it up, find the area of this sector, find the area of that sector, right? Finding each of these guys. And I've made a mess, so let me undo that. Let's do it again. So as you're drawing out sectors, now let's go. I'll draw a sector that looks like that. Do you see this one little sector? Is going to hit the circle on the outside and it's going to hit the cardioid on the inside. Outside, inside, and even this guy and that guy, and it looks like it's barely going through that cardioid, but for each of them, outside is the circle, inside is that cardioid. So that's how I know that the outside is the circle, r equals 1, and the inside is the cardioid. So that's how I know which one is R2 and which one is R1. All right, so I've got 1/2, put the integral symbol. I'm going to fill in my limits in a minute. 1 squared, which is your R, minus 1 minus cosine of theta squared. So R2, R1. Now, here's the deal. You can simplify things, especially with polar graphs with symmetry, is that you see that this little section, I colored it in, this top half of the shaded area is identical to the bottom half. And so we can simplify our problem by just doing, finding just the top half of this area and then doubling it, because then we've got both of these guys. So then my 2's cancel. Nice. And what we want to find now is our limits of integration, right? And so what we want to know is, where are these guys intersecting, right? Well, you want to find out, like, okay, the first point is here. Like, when is the cardioid equal to 0? Right here. And so you set 1 minus cosine of theta equal to 0. What you're finding is where these two guys intersect. Nope, not where they intersect, because I'm only finding this guy. So we're only finding above here. So I want to start when your r is 0, right here. Setting the cardioid equal to 0 will give me when cosine of theta is 1, which gives you theta equals 0. And then you also want up here, right, which is where they're actually intersecting right there. So this guy will go, and you'll be drawing out lines from here and all the way until you reach this guy, which is when r is 1. So you set 1 equal to theta, and so obviously your theta is either pi over 2 on this guy or 3 pi over 2. That will also give you when cosine is 0. I solved for this guy. And but obviously 3 pi over 2 is down here. I'm going to use pi over 2, this guy. And so those will be my limits of integration. 0 is my lower limit. Oop, I did not mean to do that. And exit. Sorry about that. Oh, keep hitting buttons. All right, so limits of integration are from 0 and then pi over 2. And we'll just hit some F and int on that. Again, you could totally do this by hand. I showed you how to do it on the first guy. These 2's cancel. You put F in it, and you should get 1.215. All right, that was the last new lesson. Yay! That's it. That's all brand new lessons. Tomorrow I'm going to give you some problems to try on your own and maybe work with a friendly friend, right? And anyway, but that's it. You have learned. Well, I have given you all of the content of AP Calculus BC. Give yourselves a hand. Pat on the back. You've learned all of the material for AP Calc BC. Nice! Now you're ready for the AP exam. Boom! Yes! All right. You all have a fabulous day. Maybe if I can get back over here. Stop the recording. Have a good one, guys. Bye!